we'll proceed in vector and energy calculus. Vector and commercial calculus, probably we will end today's discussion and we'll proceed upon some kind of case study. So that is the idea for the vector as far as calculus is concerned. Okay, then net idea is to proceed in artificial intelligence, how vector and calculus algebra, they are being used in AI kind of scenario. Anyway, what we have seen till now in vector and commercial calculus, vector and energy calculus, we have calculated flux from the velocity. If there is a radiation, there is a liquid, there is a liquid that is flowing and it is passing through a surface. If this is the surface and liquid is passing through, then how much is the throughput? How much is the volume of the liquid that is coming out of the surface? Velocity into the surface area is the velocity into the surface area is the net volume that is coming out of the surface. So this much we have seen. This is also called flux. This is also called flux. What is the net flux? Flux means velocity into area or velocity vector dot product with the area vector. Velocity vector dot product with the area vector. Okay, so that is called net flux coming out of it. If this is the surface and this is the surface vector, then velocity must be in the direction of the surface vector to have the maximum throughput. Otherwise, velocity vector, if it is in this direction and surface vector is in this direction, it makes this much angle. Then it will be velocity vector dot product with the surface area vector. So that is the net concept. That is the net concept of the kind of flux calculation. Velocity vector dot product or the vector field vector velocity vector is called vector field because it is a variable vector. It is algebraic vector. If it is algebraic vector, dot product with the area vector gives the net flux coming out of it. If it is really algebraic, means it is in xyz, area vector is also in xyz, then there comes a formulation there. If we are multiplying two things, dot product means this dot this, this magnitude vector. If there is a vector A and vector B and we are doing dot product, A's magnitude, B's magnitude, cos theta, that is the dot product. Means more or less is it multiplication of the magnitude only, cos theta, if they are in not in the same direction. If there is a multiplication of two items, if there is multiplication of two items, then we consider that we are in phase of calculating area. Okay, how so boldly you can say that? This is what the calculus starts from, begins from. Calculus begins from multiplication. If you are multiplying two items, then if it is algebra and one item is independent and one item is dependent upon other, then it will lead to area calculation. Anyway, multiplication with area calculation, very few people, they kind of understand this. Multiplication is nothing but area calculation. A into B, 4 into 5, 20. I know it is 20. Unknowingly, you calculated the area of a rectangle whose one side is 4 and one side is 5, or one side is 5 and one side is 4. 4 into 5. 4 into 5, one side is 5, one side is 4. This is what you did. Multiplication means calculation of a rectangle whose one side is 4 and one side is 5. One side is 4, height is 4. Instead of 5, I can say 5x, just x. Then 4 into x is the area where x is variable. If height is also height, now I can say instead of now width is x and height is x, then area is x square. All right. But if the height that is x is actually dependent upon this x is x axis and height is dependent upon x-axis. If I say x and x is 0 along x-axis, at the origin height is 0. If x is 4, then height is 4. X is 6, then height is 6. It makes a kind of triangular area. The region that is formed when the y component, the height component, is algebra and it is dependent upon x component. In that sense, if I multiply x with x, then net area will be x square by 2 as per the triangle area. This here we start entering into integral calculus. Multiplication of algebra when one is dependent upon other. When we multiplication of any two items, we can do it through area manipulation also. But if both are both operands are independent to each other, then we can go direct multiplication. But one is dependent upon other, and then we go in a graph manner, then it won't be a rectangle. It may not be a rectangle. Okay, if both are independent to each other, certainly it will be a rectangle. You can just simply multiply and get the area. But if one component is dependent upon other component, then certainly it will not be, it may not be rectangle. It can be any shape. Y is sine x and x is anyway x-axis. What is the multiplication of sine x into x, where sine x is dependent upon x? Then this is x-axis and sine x will be like this. This area we are trying to calculate with sine x into x. Then it is sine x dx. Now similarly, if we are trying to calculate the flux, then one is the velocity vector and one is area vector. Again multiplication is there. And consider the area is independent component and velocity is dependent component. Consider like that. Then it becomes velocity vector dot product d of area vector, because one is independent and one is dependent. It falls in integral calculus. Velocity vector dot d of area vector or d of position vector of area. Okay, that falls in integral calculus. Here, independent component, if I talk about area and area, then area independent component can be any of the three or combination of three x, y, z. If it is area, then along x, y plane, I am thinking about independent component. Now it is velocity vector or f dot d of area vector or position vector that talks about the area. Okay, if that is the case, I think many times we have demonstrated this. Consider this ball is centered at the origin, and at the origin there is a charge. There is an electric charge that is kept at the origin. All through electrical wave is coming out. So from the surface, electrical wave is coming out. The velocity vector of the electrical charge is all around. This is radius vector all around. It is passing through the surface. At any moment, this is the area vector that is perpendicular to the area. Velocity vector dot product with the area vector, or velocity vector dot product. If this is point, any point P, I take x, y, z, then this is position vector of that point. Then d of position vector. D of position vector of the area. Area is variable everywhere. If this is the ball and this is xy plane, depending upon the x and y, we have the height, and then there we have the area. So area is dependent upon x and y. We can say like the net flux is velocity vector dot product with the d of area position vector. That we have seen it is same as d of p is dp by dxy plane into dxy plane, and that comes as dp by dx cross dp by dy. Position vector is xi plus yj plus zk. Then dp by dx is I plus dz by dxk cross j plus dz by dyk. Dx dy, that is dxy plane. It is settled at minus dz by dxi plus minus dz by dyj plus k dx dy. This whole is area vector. Now this is very in high class scenario that we have talked about it. The area vector is dz by dx, and someone would say if I take position vector from the center, If I take any point P and from center of this sphere, if I draw a line, then this is the position vector. But area vector, if I take, that is perpendicular, both are in same direction. So if I have a surface area, then position vector and area vector are in same direction. Not necessarily true. Okay, but area vector is certainly not on the surface. If this is the surface, then area vector is not on the surface. Area vector is perpendicular to the surface. But if it is a sphere, then position vector and area vector, they are in same direction. Okay, but it can be a coincidence only. Like consider, take a plane called z equal to 2. This is xy plane. This is xy plane. On top of it, height 2. There is a plane called z equal to 2. Z equal to 2 is a plane. Now, if this is, consider, consider this is xy plane and there is a plane above here that is z equal to 2. This is the origin. Let's take any point here P on the z equal to 2 and take this position vector. Now I'm going to take area vector. Area vector will be perpendicular to the plane. Okay, so area vector, if this is the plane here, then area vector will be perpendicular to it. It will be in z direction, whereas position vector at every point it differs. Make sense? But anyway, what is the flux coming out of it? What is the area vector for the calculation of the flux? Flux area vector is d of position vector. This is what we have seen. D of position vector. That is same as dp by dxy plane into dxy plane. At the end, the area vector comes as minus dz by dxi minus dz by dyj plus k dx dy. This is the area vector. Now, if I take a plane like this, z equal to 2, what is dz by dx? If I change along x-axis, then z is not changing. It is fixed. dz by dx is 0. dz by dy is 0. Only k is there. dx, dy, k. Means area vector is always in k direction. Whereas position vector, if I take, if this is the surface, every point position vector is different. But area vector is always perpendicular. So, it is not guaranteed that position vector and area vector will be in same direction. But for a sphere, it is like that. Anyway, this is called flux. There is something called flux density. If I know the flux coming out of a volumes, coming out of a closed surface, then if flux is coming out of a closed surface, divide it by the volume, that is called flux density at a particular point, means where volume tends to 0. If this volume tends to 0, then it will shrink at origin. At origin, there will be a very minute point, consider, which has no dimension. At that point, what is the divergence or what is the flux density? At that point, what is the tendency of the point to, to throw the electromagnetic radiation all around? That is called divergence at that point. That is called divergence at that point. If liquid is coming at that point, then it is called negative divergence, like a black hole. If liquid is gushing out from that point, then it has positive divergence like sun. Okay, so that is the flux density or divergence is the net flux coming out of the surface divided by the volume. Or if the if any energy has electromagnetic velocity, then and it has that is represented as F vector, then it is F1I plus F2J plus F3K, dF1 by dx plus dF2 by dy plus dF3 by dz. This is the net divergence at particular point. This will result in an algebraic equation set that point, like x square plus y square, like the velocity vector is x square I plus y square j plus z square k. What is flux density? If that is the velocity, then consider this is centered at the origin. Now calculate the net flux coming out because of the liquid velocity, that is x square I plus y square j plus z square k. For this spherical region, divide it by the volume of this, that will give the flux density. If it is cumbersome, then df1 by dx plus df2 by dy plus df3 by dz. Someone can calculate, that will come as 2x plus 2y plus 2z. That is flux density. If someone knows, so someone can calculate flux density or divergence from the flux. from the flux density and divergence, someone can get back the flux. That is the idea. Anyway, we will have one example where we calculate the flux from the flux density. Consider there is a flux density called 4. Flux density is 4. If flux density is 4, then what is the flux? Flux can be anything. Flux can be xi plus yj plus 2zk. Then it is df1 by dx plus df2 by dy plus df3 by dz. Okay, if that is the scenario, then it is again 4, or it is 4xi, or it is 4yj, or it is 4zk, whatever it is. So consider the flux density is 4. Okay, and now I have on xy plane, I have a circle that is designated by x square plus y square equal to 2. Now the exercise what we will do now, let's calculate the flux. Let's calculate the flux from the flux density. Let's calculate the flux from the flux density. So consider that there is a circle, this is xy plane and origin is in blue color. So this is xy plane and one circle is kept like this. This is a mere a line. Don't consider it is a thick and it is a volume. This is mere a line. Now there is a flux density of 4. Then what is the flux that is passing out of this this curve? Okay, if someone wants to calculate flux density, flux from the flux density, then it is flux density into the volume is the net flux. Flux density is flux divided by the volume. Flux is flux density into the volume. Again multiplication has come. Flux density and volume, two are getting multiplied to each other. Flux density and volume, they are multiplied with each other. In that case, one is dependent and one is independent. Flux density is dependent and volume is independent. In that case, it very higher term. Okay, in very higher term, but actually xyz is independent and flux density is dependent upon them. But rather than going for three independence, let's say I have a independent volume. I have talked about it. If 2d, if there is a 2d and there is a x axis and y axis, then y is dependent upon x axis. If it is a 3d, then there is a z axis and xy plane, then z axis is dependent upon xy plane. This is 3D. If it is 4D, mind it, I have only one independent component we are talking. If it is 4D, then it is also called density function. In that sense, the density is dependent upon xyz volume. Density is dependent upon xyz volume. That is the density. It is dependent upon xyz volume. So if I am calculating flux from the flux density, then flux density into volume is the net flux. One is dependent, that is flux density, independent in xyz or xyz volume or volume. So net flux is flux density into not V, d of V. It falls in integral calculus when we are multiplying two algebra and one is dependent upon other. Then it falls in area calculation, knowingly, unknowingly, where one width is volume and height is density. Anyone would say how width can be, how volume can be width. Volume is three dimensional, but we have shrunk into one dimension. So now volume is x-axis and height is density. Now it is again multiplication of density and volume. It is again multiplication of density and volume. If that is the scenario, then the flux density into d of v is the net net multiplication, where integration limit is volume 1 to volume 2. The way we calculate area x-axis and y-axis. Y-axis I draw a graph against x-axis and we are trying to calculate the area. from what x to what x. This is trillion-dollar explanation of any two multiplication. If you get any two multiplication, you can bring in calculus there. That's where calculus started, where one is dependent and one is independent. So here independent is volume, dependent is the density. Volume from V1 to V2. Now if I draw graph, then x-axis is volume and y-axis is density. Depending upon the volume, density may differ. Okay, depending upon the volume parameter, density may be different. Okay, in that sense, volume into density is the net area of this graph from volume 1 to volume 2 on the x-axis. But at different volume, how density can be different? Can you just visualize it? Yes, I can visualize it. Now, consider this is centered at the origin. This is centered at the origin and it has a volume. Now, in this is inside this, there is there is a kind of mix of metal. At some places gold is there, at some places zinc is there. Okay, at some places lead is there, at some places iron is there. Everyone has different density. In that sense, inside this, if you take any coordinate x comma y comma z or x0 x1 y1 z1, at that point if you find a lead, then their density is different. If you go to another coordinate x1 x2 y2 z2 and there you find iron, density is different. If you go to another x3 y3 z3, if you go to another volume point, another point in the volume, you may find gold out there. Density is different. Similarly, if I take x-axis as volume at different volume point, the density is different. Okay, density into volume will give the net weight. Okay, how much is the net weight from volume 1 to volume 2? Calculate the area, that is the density into volume. If density is dependent upon the volume, then density that is the height, it may not be a flat line. If it is a flat line, you can simply multiply it. That is a rectangular area. If it is not a flat line, it is some curve out there. It is varying depending upon the volume. If you proceed, then you have to use density into d of v. Density into volume will not work. Okay, this is a trillion-dollar expression because here only calculus enters. At this point only calculus enters. But nowadays people go for calculus as delta x, delta y, delta z, and from differentiation they try to enter into calculus. But actual calculus entered through integral calculus, not from differentiation. Okay, integral calculus means multiplication, differential calculus means division. The basic of mathematics is addition, and multiplication is more near to addition than division because division is near to subtraction and then subtraction is near to addition, whereas multiplication is directly near to addition. This proves that integral calculus came first, then differentiation came. Okay, multiplication came first, then division came. So this is the basic of primitive calculus. So flux density and volume. So flux density into volume. Now we are trying to calculate flux from the flux density 4 when there is a I draw a line on xy plane at x square plus y square equal to 9. If that is there is a circle on xy plane, then what is the flux? Now flux density, when we are going for the term flux density is calculated in a closed surface. In a closed surface, may not be a sphere. In a closed surface, what is the flux coming out of the surface divided by the volume of the surface, where volume tends to zero. If I shrink this, if I shrink any closed surface, shrink, because volume tends to zero, it will come to a point, but point is still be a 3D, three dimension. That point will be three dimension. And there we shrink this flux calculation by the volume. If I am saying my flux density is 4, then it is talking about a point that is 3D. And there what is the flux density? If I am trying to calculate the flux of a line, circular line on xy plane, then it is invalid statement because there has to be a volume. If I want from a flux density, if I want a flux, then at a point what is flux density? Then around that point I have to create a closed surface, not necessarily a cubical surface. It can be a sphere, it can be any surface, but it should be completely closed around that point, and then calculate the flux, divide it by the volume. That I have got as flux density. I am calling it as flux density. Flux density into volume is the net the kind of flux, but there is no volume. There is only a circle for which there is a surface area, no height is there. In that case, this statement is invalid. If I have a flux density, I am trying to calculate the flux for a surface that is a circular surface on xy plane. It has to be a volume. Anyway, you are talking so many things. Now, can you calculate the flux coming out, coming flux coming? Consider there is a flux density called x square plus y square plus z square plus 3. This is flux or flux density. This is flux density. Consider there is a flux density called x square plus y square plus z square plus 3. This is flux density. Now, can you calculate flux? That is flux. Can you calculate a flux through a volume? Flux. Now, flux I have to calculate through a volume. If I take any haphazard volume, then flux will be calculated against the outside surface of that volume. If I have flux density, if I have a flux density around at flux density is calculated at a point. If I have a flux density at a point, I create a closed surface around it, making it a volume. What is flux that is passing out of it? Because there is a point inside it which is has a divergence. Flux density is there. Consider there is a point and its flux density is x square plus y square plus z square plus 3, that is flux density. Now I have a volume, one volume that is defined by one surface, that one circle, one spherical surface which has radius 1, another spherical surface which has radius 2. In between, I have given this example last time, but there flux density was 0. In between, if there is a sphere and there is an outer sphere from it, and it is at the center of the sphere, there I have flux density as x square plus y square plus z square equal to 3. If there is an outer sphere of it, then in between there is a solid region. Inside that solid region, there I have to calculate the flux, but flux will be calculated for the surface, not the solid region. So if there is a solid region in between two sphere, then it will have two sides. One side is out the one side of the solid region is the surface of the bigger sphere, and other is the surface of the inner sphere. This is how the surface would be. Calculate the flux coming out of it. Flux will come out from the inner surface, but flux will go toward the center. One will flux will go outside the center. Anyway, both sphere are oriented outward. This sphere is oriented outward, and bigger sphere is also oriented outward. Now for that, in the central region, volume region, calculate the flux. Now flux is flux density dot d of v. D of v is dx dy dz, and then the flux density is x square plus y square plus z square. Okay, plus 3 dx dy dz, where x is, now where is x here? Where is x here? Now if someone calculate the x, then x is, consider the bigger sphere is radius 2 and inner sphere is radius 1. X is minus 2 to minus 1. X is minus 2 to minus 1. To 1 to 2. Y is a circular region on xy plane. There minus a square root of a square minus x square to square root of a square minus x square, where a square 1 is 2 and 1 is 1. To other side, square root of 1 square minus x square to square root of 2 square minus x square. What is z? What is z? How much it is? Z is now variable in x and y. Lower is minus a square root of 1, 2 square minus x square minus y square. 2 square minus a square root of 1 square minus x square minus y square. 2, 2 square root of 1 square minus x square minus y square. 2 square root of 2 square minus x square minus y square. This is the net, something like that. This is the net flux. This is the net calculation of the flux. Okay. Now, someone can try calculating it. So, how much? I have never tried, but how much it would be? Okay. Someone would say, why you are doing that much? Now, if there is an inner surface and its outside flux is like this, it is oriented like this, and inside it the source is kept, the energy source is kept inside it, then this surface, outward surface, will not come into the picture as far as calculation of this solid region is concerned. Inner surface will come into the picture. So the direction of the inner, if this is the volume, inner volume, the direction of this volume will be toward the center. Means it will be negative. It will be negative. Whereas outside it will be positive. Calculate this flux and make it negative. Calculate the outside flux, make it positive and add it. Or simply calculate two flux and subtract, because the direction is different. So outside flux is x square plus y square plus z square plus 3 dx dy dz, where limit holds minus 2 to 2, that is x. Y is minus 2 square minus x square square root 2 square root 2 square minus x square. Z is minus a square root 2 square minus x square minus y square. 2 square root 2 square minus x square minus y square. Calculate the flux and calculate the flux that is inside where radius is 1. Okay, now try both and subtract it. We will do in next session, but it will come in the topic of case study. So we will end up commercial calculus because we have finished everything. So net flux, net flux through the closed region is 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 the kind of whatever the volume we have multiplied by the flux density. It is same as the inner volume, same as the outer volume and flux density, that is outer flux minus inner volume and inner flux density. Someone can try full what at the beginning we said. This strip, this strip, this strip, this strip, and this strip, this strip. That also someone can try and validate if result is safe. We will do more example, but vector and commercial calculus we are ending up because all topic we have covered. There is nothing left for it. So that way we will proceed in the case study. Don't mind supporting us. +91 is the India country code. 9483160610 is the telephone number. 9483160610 is the telephone number. +91 is the India country code.